Tonight, as you settle into the quietness of your room, imagine stepping outside and looking up at the star-filled sky. Each pinprick of light that meets your eyes has traveled across unimaginable distances to reach you, carrying stories written in photons and time, but hidden within that gentle starlight are secrets that astronomers have only recently learned to read. The presence of worlds we cannot see, planets orbiting distant suns in a cosmic dance as old as the universe itself. You are about to become a detective of the cosmos, learning the art of finding invisible worlds. This is not the kind of detection you might imagine from movies, with dramatic revelations and sudden discoveries. Instead, it is a patient, gentle practice of watching and waiting, of reading the subtle language that stars speak when they harbor planetary companions. It is science at its most poetic, where the smallest changes in light become doorways to entire worlds. Consider for a moment how extraordinary this quest truly is. The planets we seek to find are not just far away, they are impossibly far away. The nearest star to our Sun, Proxima Centauri, sits more than 4 light-years distant. If our Sun were the size of a basketball, Proxima Centauri would be another basketball sitting 3,000 miles away. And the planets we're looking for, they would be grains of sand orbiting those distant basketballs, completely invisible to any telescope we could ever build. Yet we have found them. Thousands of them. We have mapped their sizes, calculated their masses, determined their temperatures, and even begun to analyze the chemical composition of their atmospheres. We have done all of this without ever seeing a single one directly, using methods so elegant and indirect that they feel almost like magic. The story begins with a simple truth. Every star and planet in the universe is engaged in a gravitational conversation. When you walk across a room, you are pulling on every object around you with your own gravity, and they are pulling back on you. The effect is so small as to be immeasurable, but it exists. Scale this up to cosmic proportions, and something beautiful happens. A planet orbiting a star doesn't simply circle around a stationary object. Instead, both the star and the planet orbit around their common center of mass, like two dancers spinning together. Picture this cosmic ballet in your mind. Our Sun, massive, beyond comprehension, is not perfectly still. Jupiter, though tiny in comparison, is still massive enough to make our Sun wobble slightly as it orbits. If you could watch our solar system from a distant star, you would see our Sun trace a small circle in space every 12 years. Jupiter's orbital period. This wobble is so subtle that the Sun moves only about the width of its own diameter, but it moves nonetheless. This is your first clue in the cosmic detective story. Every star with planets performs this same subtle dance, wobbling in response to the gravitational tugs of its invisible companions. The larger the planet, or the closer it orbits to its star, the more pronounced this stellar wobble becomes. By watching stars with incredible precision over months and years, astronomers can detect these tiny motions and infer the presence of worlds they cannot see. But the universe offers us other clues as well, written in the language of light itself. Sometimes, from our perspective on Earth, a planet passes directly between us and its star, what astronomers call a transit. When this happens, the planet blocks a tiny fraction of the star's light, causing it to dim by the smallest measurable amount. Imagine holding a grain of sand in front of a searchlight. The dimming would be almost imperceptible, yet with sensitive enough instruments, it can be detected. These transits tell us remarkable stories about distant worlds. The amount of dimming reveals the planet's size. Larger planets block more light. The duration of the transit tells us about the planet's orbital speed and distance from its star. If we're fortunate enough to observe multiple transits, we can determine the planet's orbital period with extraordinary precision. Each transit becomes a cosmic timestamp, marking the passage of an invisible world across the face of its Sun. There is something deeply moving about this process of discovery. In an age when we often feel that everything has been explored and mapped, the search for exoplanets reminds us that we are still pioneers. Every night, telescopes around the world and in space point toward different patches of sky, watching tens of thousands of stars with robotic patience. They measure brightness changes so small that they would be like detecting the dimming caused by a single firefly crossing in front of a stadium's floodlights. The dedication required for this work is profound. Some of the planets we've discovered take hundreds or even thousands of Earth days to complete a single orbit around their stars. To confirm their existence, astronomers must watch for multiple transits, sometimes waiting years between observations. It is science practiced with the patience of a monk and the precision of a watchmaker. As you lie here tonight, consider that this gentle hunt for hidden worlds is happening all around us, all the time. Radio waves carrying data from space telescopes are passing through your room at this very moment, carrying information about distant stars and their wobbles, about tiny dimmings in starlight that occurred years ago and are only now being detected and analyzed. This search has revealed something extraordinary about our universe. Planets are everywhere. Almost every star you can see in the night sky has at least one planet orbiting it, and many have entire systems of worlds. The galaxy is not the cold, empty place we once imagined, but a cosmic archipelago of planetary systems, each one unique, each one a complete world with its own story of formation, evolution, and perhaps even life. The methods we use to find these worlds are just the beginning of our story. Each technique, the patient watching for stellar wobbles, the careful measurement of dimming starlight, opens a different window into the nature of these distant planets. But to truly understand how we decode the secrets hidden in starlight, we must listen more carefully to what the stars themselves are telling us, learning to hear the whispers carried in every beam of light that reaches our telescopes. In the quiet moments before sleep, as your breathing settles into a gentle rhythm, imagine that you could hear the secret conversations happening between stars and their hidden planets across the galaxy. These are not voices as you know them, but whispers written in light itself, subtle tremors in starlight that tell stories of gravitational dances performed in the cosmic dark. Tonight, you learn to listen to these stellar whispers with the ears of an astronomer, discovering how every star betrays the presence of its planetary companions through the most delicate movements, recorded not in sound, but in the shifting colors of light that travel across billions of miles to reach our telescopes. Picture a street musician playing violin on a busy corner. Even from a distance, even with your eyes closed, you can tell when they move as they play. Their footsteps, their swaying, the subtle changes in their breathing all affect the sound that reaches your ears. The music itself carries the story of the musician's movement, encoding their dance in frequencies and rhythms that your ear can detect. If you know how to listen, stars perform a similar dance, but instead of music, they speak in light. When a massive planet orbits a star, both objects actually orbit around their shared center of gravity, a point called the barycenter. If the planet is large enough and close enough to its star, this gravitational ballet is the star to wobble back and forth in space with the same rhythm as the planet's orbit. From Earth, we cannot see this wobble directly. The stars are far too distant for us to observe their physical motion across the sky. Instead, we detect something far more subtle, the Doppler effect in starlight. You know this effect from everyday life. When an ambulance approaches you, its siren sounds higher in pitch because the sound waves are compressed as the vehicle moves toward you. When it passes and moves away, the pitch drops because the sound waves are stretched out. Light behaves in exactly the same way when a star wobbles toward us due to the gravitational pull of an orbiting planet. Its light becomes slightly bluer, the wavelengths are compressed. When the star wobbles away from us, pulled by the planet on the opposite side of its orbit, the light becomes slightly redder, the wavelengths are stretched. This shift is incredibly small, sometimes just a few meters per second in a star's motion, which translates to wavelength changes measured in billionths of a meter. To put this in perspective, imagine trying to detect whether someone walking across a football field is moving toward you or away from you, but you're watching from a distance of 10,000 miles, and the person is only moving at the speed of a leisurely stroll. The precision required is almost incomprehensible. Yet modern spectrographs can measure these tiny color shifts with extraordinary accuracy. The beauty of this method lies in what these stellar whispers reveal about the invisible worlds causing them. A large planet creates a larger wobble in its star, producing a stronger Doppler signal. A planet orbiting close to its star completes its gravitational dance quickly, causing the star's light to shift from blue to red and back again in a matter of days or weeks. A distant planet takes years to complete one orbit, creating a slow, stately rhythm in the star's spectral song. As you rest here tonight, consider the patient work required to decode these messages. Astronomers must observe the same stars night after night, sometimes for years, building up a library of spectral measurements that gradually reveals the gravitational choreography happening around distant suns. They look for patterns, the regular rise and fall of velocity measurements that indicates a planet's orbital period. But the universe rarely makes things simple. Many stars have multiple planets, each adding its own voice to the stellar chorus. Imagine listening to a symphony where each instrument represents a different planet, each playing at its own tempo determined by its orbital period. A system with 3 planets might show overlapping velocity curves, the rapid oscillations of an inner world, the slower rhythm of a middle planet, and the stately progression of an outer giant. Disentangling these combined signals requires both sophisticated mathematics and intuitive understanding of celestial mechanics. The radial velocity method, as astronomers call this technique, has revealed some of the most surprising discoveries in exoplanet science. The first confirmed exoplanet around a Sun-like star, 51 Pegasi b, announced itself through exactly this kind of stellar whisper in 1995. The discovery shocked astronomers because the planet was massive, about half the mass of Jupiter, but orbited its star every 4 days, closer than Mercury orbits our Sun. This hot Jupiter challenged everything scientists thought they knew about planetary formation. Since then, radial velocity measurements have revealed planets of all kinds, super-Earths with masses several times our own world, Neptune-sized planets in scorching close orbits, and Jupiter-mass giants in the outer reaches of their systems. Each discovery adds another note to our understanding of how planetary systems form and evolve, showing us that our own solar system is just one variation on cosmic themes played out around thousands of different stars. The most remarkable aspect of this method is its sensitivity to the gravitational relationships between worlds. When multiple planets orbit the same star, they influence each other's motion through their mutual gravitational attraction. These planet-planet interactions create subtle variations in the timing of transits or additional complexity in radial velocity curves. By carefully analyzing these gravitational conversations, astronomers can determine just that planets exist, but how they interact with each other across the depths of space. There is something deeply meditative about this process of discovery. In our daily lives, we are surrounded by noise and urgency, but the search for exoplanets requires a different kind of attention. The patience to watch the same stars for months or years, waiting for the subtle patterns to emerge from the data. It is science practiced at the pace of celestial mechanics, where orbits unfold over seasons and years rather than minutes and hours. As you settle deeper into rest, imagine the countless stellar conversations happening at this very moment across our galaxy. Every clear night, telescopes around the world point toward thousands of stars, collecting photons that left those distant suns months or years ago. Each spectrum captured tells part of a story about worlds we may never visit, but can know through the gentle trembling of starlight. The radial velocity method has given us our first glimpse into the gravitational architecture of distant planetary systems, but it tells us only part of each world's story. To truly understand these hidden planets, their sizes, their atmospheres, their potential for harboring life, we must learn to read other messages written in starlight. Messages that arrive when worlds pass like shadows between us and their brilliant suns. In the stillness of your bedroom, as shadows from passing clouds drift across your window, you are witnessing something that happens on a cosmic scale around distant stars throughout our galaxy. Tonight, you discover how entire worlds reveal themselves through the simple act of casting shadows, creating eclipses so subtle they can only be detected by the most sensitive instruments ever built. The beauty of planetary transits lies in their elegant simplicity. When a planet's orbit is aligned just right from our perspective on Earth, it passes directly between us and its star, blocking a tiny fraction of the star's light. This celestial eclipse creates a characteristic signature, a gentle dimming, that lasts 4 hours as the planet crosses the stellar disk, followed by a return to full brightness as the world moves beyond the star's edge. Imagine holding a coin at arm's length in front of a distant streetlight. The coin blocks some of the light, creating a shadow that falls across your face. Now imagine that coin is a planet. The streetlight is a star hundreds of light years away, and the shadow falls not on your face, but on our entire solar system. The dimming is so slight that a star might fade by only 1/100%, but sensitive photometers can detect this whisper-quiet change with remarkable precision. The first confirmed transit of an exoplanet was observed in 1999, when astronomers detected the passage of HD 209,458b across its star. The planet, a hot Jupiter orbiting extremely close to its Sun, caused its star to dim by 1.7% for just over 3 hours. This observation was revolutionary, just because it confirmed the planet's existence, but because it provided the first direct measurement of an exoplanet's size. By knowing how much light the planet blocked, astronomers could calculate its radius with extraordinary accuracy. As you rest here in the quiet darkness, consider the cosmic choreography required for a transit to occur. The planet's orbital plane must be tilted at exactly the right angle for it to pass between us and its star. From our perspective, most planetary systems are tilted either too far toward us or too far away, so we see their orbits edge on rather than face on. Only about 1% of planetary systems are aligned correctly for us to witness transits, making each detection a fortunate accident of cosmic geometry. But when the alignment is perfect, transits become windows into the detailed properties of distant worlds. The depth of the transit, how much the star dims, tells us the planet's size relative to its star. A larger planet blocks more light, creating a deeper transit. The duration of the transit reveals information about the planet's orbital speed and distance from its star. A planet in a tight orbit moves quickly across the stellar disk, while a more distant world takes longer to complete its crossing. The shape of the transit light curve carries even more subtle information. As the planet begins its journey across the star, it first encounters the star's limb, the edge where the stellar disk meets space, because stars are not uniformly bright. Across their surface, being slightly dimmer at their edges due to atmospheric effects, the initial dimming is gradual rather than abrupt. Similarly, as the planet completes its transit, the brightening is gradual as it passes beyond the opposite limb. These subtle variations in the transit shape allow astronomers to measure the planet's orbital inclination with remarkable precision, and sometimes even detect the presence of an atmosphere. When a planet has a substantial atmosphere, starlight passing through it can be absorbed at specific wavelengths, creating tiny additional dips in the light curve that reveal the chemical composition of the world's air. The most remarkable transit discoveries have come from space-based telescopes that can monitor thousands of stars simultaneously with unprecedented precision. The Kepler Space Telescope, launched in 2009, stared at a single patch of sky containing over 150,000 stars for nearly 4 years, measuring their brightness every 30 minutes. This patient vigil revealed over 2,600 confirmed planets and thousands more candidates, transforming our understanding of planetary systems. Kepler's discoveries revealed that planets are incredibly common throughout our galaxy. Small, rocky worlds are particularly abundant, with many systems containing multiple planets packed into orbits closer to their star than Mercury is to our Sun. These compact systems challenge our understanding of planetary formation and migration, showing that solar systems can be organized in ways completely unlike our own. The transit method has also revealed some of the most exotic worlds in our cosmic catalogue. There are planets that orbit their stars in just a few hours, tidally locked with one side permanently facing their sun in scorching daylight, while the other side remains in eternal frozen night. There are worlds orbiting binary stars, experiencing double sunsets, like scenes from science fiction. There are planets with such elongated orbits that they experience extreme seasonal variations, swinging from freezing cold to molten hot over the course of their years. Perhaps most intriguingly, transit observations have detected planets in the habitable zones of their stars, the orbital distances where liquid water could exist on a world surface. These potentially habitable worlds show up as gentle dimmings lasting many hours as they cross their smaller, cooler red dwarf stars. Each transit of such a world is a reminder that somewhere in the galaxy, seasons might be changing on a world not entirely unlike our own. The precision required for transit detection is almost beyond comprehension. Modern space telescopes can detect brightness changes as small as 20 parts per million, equivalent to distinguishing between a lighthouse at full brightness and the same lighthouse with a single candle snuffed out. This sensitivity allows astronomers to find planets smaller than Earth around stars dozens of light years away. But transits offer us more than just detection and measurement. They provide our best opportunity to study the atmospheres of distant worlds. During a transit, some of the star's light passes through the planet's atmosphere before reaching Earth. Different atmospheric gases absorb light at specific wavelengths, creating a molecular fingerprint that can be detected in the combined light of the star and planet. Through this technique, called transmission spectroscopy, astronomers have detected water vapor, methane, carbon dioxide, and other molecules in the atmospheres of Exoplanets and ETS. As your thoughts begin to drift towards sleep, imagine the delicate dance of shadows happening right now across the galaxy. Somewhere, a world perhaps not unlike Earth is beginning its slow journey across the face of its star, creating a dimming so gentle that it would be invisible to the naked eye, but clear as day to our robotic sentinels watching patiently from space. The transit method has opened our eyes to the shadows cast by distant worlds. But these eclipses are just one part of a larger gravitational story. To fully understand the invisible forces that shape planetary systems, we must listen to the deeper conversations between worlds and their stars, learning to detect the subtle tugs and pulls that govern the cosmic dance of gravity itself. In the gentle darkness of your room, as you feel the familiar weight of your body settling into your bed, you are experiencing the most fundamental force in the universe, gravity. Tonight, you become fluent in gravity's ancient language, learning to read the conversations between distant stars and their invisible companions across the vast reaches of space. Gravity is perhaps the most patient storyteller in the cosmos. It speaks without words, writes without ink, and leaves messages that can be read across billions of years and trillions of miles. Every mass in the universe, from the smallest pebble to the largest star, participates in an ongoing dialogue conducted entirely through the gentle but inexorable pull of gravitational attraction. When you learned about radial velocity measurements earlier, you glimpsed how this conversation works. Now, you dive deeper into the nuanced grammar of gravitational communication, discovering how astronomers have become translators of forces that cannot be seen, only felt through their effects on light and motion. Picture two figure skaters holding hands as they spin together on ice. The larger skater remains relatively stationary at the center of their rotation, while the smaller one whirls in a wide circle around them. But look more carefully, and you'll notice something subtle. The larger skater is not perfectly still. They wobble slightly, tracing a small circle in response to the gravitational pull of their spinning partner. This is exactly what happens when a massive planet orbits a star. The mathematics of this dance are elegant in their precision. Every star-planet system has a point called the barycenter, the center of mass around which both objects actually orbit. When the planet is much smaller than its star, this barycenter lies deep within the star itself, causing the stellar wobble to be barely detectable. But when the planet is massive, or when it orbits very close to its star, the barycenter, can shift toward the star's surface or even outside it entirely, creating wobbles large enough for our instruments to measure. The beauty of radial velocity measurements lies in how they reveal us the presence of planets, but their intimate gravitational relationships with their stars, a Jupiter mass. Planet orbiting close to its star creates a different signature than the same planet orbiting at a greater distance. The amplitude of the stellar wobble tells us about the planet's mass, while the period of the wobble reveals the length of the planet's year. But gravity's conversations become even more complex and beautiful when multiple planets participate. Imagine not two figure skaters, but 3 or 4, all connected and spinning together. Each skater influences the motion of all the others, creating a complex choreography that can only be understood by carefully watching the movement of each participant over time. In planetary systems with multiple worlds, each planet adds its own voice to the gravitational chorus. A system might have a massive planet in a distant orbit, creating a slow, stately wobble in its star that takes years to complete one cycle. Closer in, a smaller planet might orbit every few weeks, adding a faster oscillation to the star's motion. Even closer, a third planet might race around its star every few days, contributing a rapid tremor to the stellar dance. When astronomers observe such systems, they see the combined effect of all these gravitational conversations happening simultaneously. The star's velocity curve becomes a complex wave, the sum of multiple periodic signals overlapping and interfering with each other. Disentangling these signals requires sophisticated mathematical techniques, but the reward is a complete map of the system's gravitational architecture. Some of the most remarkable discoveries in exoplanet science have come from reading these multiplanetary conversations. The TRAPPIST-1 system, for example, contains 7 Earth-sized planets packed into orbits smaller than Mercury's path around our Sun. The gravitational interactions between these worlds are so strong that they significantly alter each other's orbital periods over time. By carefully measuring these timing variations, astronomers can determine not just the masses of individual planets, but how they influence each other's motion through space. The precision required for these measurements pushes the boundaries of what is technically possible. Modern spectrographs can detect velocity changes as small as 1 meter per second, about the speed of a person walking slowly. To put this in perspective, if you were watching Earth from a distant star, our planet's gravitational effect on the Sun would cause it to wobble back and forth at a speed of about 9 centimeters per second, barely faster than a garden snail. This extraordinary precision has revealed some of the universe's most surprising gravitational conversations. There are planetary systems where massive worlds orbit so close to their stars that they complete full orbits in less than a day, creating velocity signals that oscillate faster than a human heartbeat. There are eccentric planets whose elongated orbits cause their stars to wobble in slow, stretched-out cycles that reveal the gravitational history of planetary migration and evolution. Perhaps most intriguingly, radial velocity measurements have detected planets around binary star systems, where two stars orbit each other while hosting planetary companions. In these complex gravitational environments, planets experience the combined pull of two stellar masses, creating orbital dynamics unlike anything in our own solar system. The velocity signatures of such systems are incredibly complex, showing the overlapping influences of star-star and star-planet gravitational interactions. As you rest here in the quiet night, consider that gravity's conversations are happening all around you, all the time. The moon pulls on Earth's oceans, creating tides that rise and fall with lunar precision. Jupiter's massive presence shepherds asteroids and comets, protecting the inner solar system from frequent impacts. Even the galaxy itself participates in these gravitational dialogues, with the collective mass of billions of stars creating the spiral arms and orbital patterns that give the Milky Way its distinctive shape. The radial velocity method has become one of our most powerful tools for eavesdropping on these cosmic conversations. Every clear night, telescopes around the world point toward thousands of target stars, collecting spectra that will be analyzed for the telltale signs of gravitational wobbles. Each measurement adds another data point to velocity curves that sometimes take decades to complete, requiring patience and dedication that spans entire scientific careers. But gravity speaks in more than just stellar wobbles. The same force that causes stars to dance in response to their planetary companions also affects the light itself as it travels through the curved spacetime around massive objects. This opens up entirely new ways of detecting and studying distant worlds, using the universe's own architecture as a vast telescope. The conversations between gravity and light create some of the most elegant detection methods in all of astronomy, where the presence of invisible worlds can be inferred not from their direct effects on their stars, but from how they bend and focus the light of even more distant objects. These techniques turn the entire cosmos into a lens, allowing us to peer deeper into space than any conventional telescope could ever achieve. As your thoughts begin to drift toward sleep, imagine the countless gravitational conversations echoing across the galaxy at this very moment. Every star system is engaged in its own unique dialogue, each planet adding its voice to a cosmic symphony that has been playing since the first worlds formed around the first stars, billions of years ago. Tonight, as you settle into the comfort of your bed, imagine the challenge of taking a photograph of a firefly hovering next to a powerful searchlight from a distance of several miles away. This seemingly impossible task captures the essence of what astronomers attempt when they try to directly image exoplanets, capturing actual pictures of worlds that are billions of times fainter than the stars they orbit, separated by distances so small they appear as a single point of light even through our most powerful telescopes. Yet against all odds, we have succeeded. In your hands tonight lie the stories of the first photographs of alien worlds, each image representing a triumph of human ingenuity over the overwhelming brightness of distant suns. These are not the detailed portraits you might imagine from science fiction, but rather precious dots of light that represent entire worlds, each photon a messenger that has traveled across the galaxy to tell us of places we may never visit, but can now, in the most literal sense, see. The challenge of direct imaging lies in what astronomers call the contrast problem. A typical exoplanet reflects only a tiny fraction of its star's light, roughly 1 part in a billion for planets like Earth, and perhaps 1 part in a million for large, reflective gas giants. Imagine trying to spot a grain of sand next to a lighthouse beam while standing 10 miles away, and you begin to appreciate the technical miracle to separate planetary light from stellar glare. The solution comes through a technique called coronography, borrowed from solar astronomy, where similar methods are used to block the sun's brilliant disk and reveal the delicate structure of its corona. In exoplanet imaging, coronagraphs create artificial eclipses, using precisely shaped masks or sophisticated optical systems to suppress the star's light while preserving the faint glow of orbiting worlds. Picture the careful ballet required for such observations. The telescope must track its target with extraordinary precision, compensating for atmospheric turbulence that would otherwise blur the star's light and contaminate the surrounding region where planets might hide. Adaptive optics systems use deformable mirrors that adjust hundreds of times per second, correcting for the twinkle in starlight that makes stars appear to dance when viewed from Earth's surface. The first confirmed direct image of an exoplanet was captured in 2008, showing a world designated to M120 be orbiting a brown dwarf star about 170 light-years from Earth. The planet appeared as a faint red dot, glowing with the heat of its formation, still warm from the gravitational collapse that created it billions of years ago. This single pixel of light represented the culmination of decades of technological development and the opening of an entirely new window into the study of distant worlds. Since that pioneering image, direct imaging has revealed some of the most photogenic planetary systems in our cosmic neighborhood. The HR 8799 system, located about 129 light-years away, hosts 4 massive planets that have been photographed orbiting their young star, ever stately gravitational dance. Time-lapse images spanning several years show these worlds actually moving in their orbits, providing the first visual evidence of planetary motion around another star. The planets we can image directly are necessarily quite different from Earth. They tend to be young, massive, and far from their star's conditions that make them bright enough in infrared light to be separated from their stellar glare. These are predominantly gas giants, often several times more massive than Jupiter, orbiting at distances comparable to or greater than Pluto's distance from our Sun. Their youth is crucial because young planets still glow with the heat of their formation, making them detectable in infrared wavelengths where the contrast with their stars is more favorable. Each direct image tells a unique story about planetary formation and evolution. The planets around H or 8799, for example, orbit much farther from their star than current theories easily explain. Their wide orbits suggest either that planets can form at much greater distances than previously thought, or that these worlds migrated outward from closer-in birthplaces through gravitational interactions with other planets or the surrounding disk of dust and gas. The colors of directly imaged planets provide clues about their atmospheric composition and surface properties. Planets that appear reddish in infrared light often have atmospheres rich in dust clouds or complex organic molecules. Those that appear more neutral in color might have clearer atmospheres that allow deeper infrared radiation to escape from their warm interiors. The technique has also revealed unexpected diversity in planetary system architecture. Some stars host single, massive planets in wide orbits, while others harbor multiple worlds arranged in complex gravitational relationships. The Beta Pictoris system shows a massive planet orbiting within a disk of dust and debris, providing a rare glimpse of what our own solar system might have looked like during its chaotic youth, when planets were still forming and migrating through fields of primordial material. Direct imaging offers unique advantages over other detection methods. Unlike transit observations, which only work when planetary orbits are aligned edge-on from our perspective, direct imaging can potentially detect planets in any orbital orientation. Unlike radial velocity measurements, which are most sensitive to massive planets in close orbits, direct imaging excels at finding distant, massive worlds that would be difficult to detect through stellar wobbles. Perhaps most importantly, direct imaging allows astronomers to study planetary atmospheres through spectroscopy. By spreading the light from an imaged planet into its component wavelengths, researchers can identify specific molecules in the planet's atmosphere. Water vapor, methane, carbon monoxide, and other compounds each absorb light at characteristic wavelengths, creating molecular fingerprints that reveal the chemical composition of alien air. The future of direct imaging promises even more remarkable discoveries. Next-generation telescopes will use advanced coronagraphs and space-based platforms to image smaller, more Earth-like planets around nearby stars. The James Webb Space Telescope has already begun taking spectra of directly imaged exoplanets, revealing detailed atmospheric compositions that were previously impossible to obtain. As you rest here in the gentle darkness, consider the photons that are traveling toward Earth at this very moment, light that left distant planets hours, days, or years ago, and is now racing across space to potentially become part of the next great direct image of an alien world. Somewhere in the cosmos, reflected sunlight from a planet not unlike our own may be beginning a journey that will end with its detection by telescopes not yet built, adding another precious dot of light to our growing album of cosmic portraits. The ability to actually see these distant worlds, even as mere points of light, transforms our relationship with them from abstract mathematical concepts to tangible places. Each image represents not just a technical achievement, but a moment of connection across the vast depths of space, proof that the universe is filled with worlds whose light can travel across the galaxy to reach our cameras, carrying messages written in wavelengths that speak of atmospheric chemistry, surface temperatures, and the endless creativity of planetary formation. Yet even as we celebrate these direct glimpses of distant worlds, the universe holds deeper secrets about planetary detection. using the very fabric of spacetime itself as a lens to reveal worlds that could never be detected through conventional means. In the quietness of your evening rest, as you gaze toward your window, where distant streetlights blur into soft halos. Through the glass, you are witnessing a principle that operates on the grandest scales imaginable. Tonight, you discover how the entire universe becomes a vast optical instrument, where gravity itself acts as a lens, bending light across cosmic distances to reveal worlds that could never be detected by any other means. This phenomenon, called gravitational microlensing, represents one of the most elegant confirmations of Einstein's theory of general relativity, transformed into a practical tool for planetary discovery. It works on a principle both simple and profound. Massive objects warp the fabric of spacetime itself, and light, having no choice but to follow the geometry of space, bends as it passes near these gravitational wells. Picture a marble rolling across a stretched rubber sheet. If you place a bowling ball in the center of the sheet, it creates a depression that curves the sheet's surface. Now, if you roll the marble past the bowling ball, its path will curve as it follows the warped surface. Light behaves similarly as it travels through the curved spacetime around massive objects like stars, following paths that bend toward the gravitational source. When this bending is perfectly aligned, when a massive star passes directly between us and a more distant background star, something remarkable happens. The closer star acts like a natural magnifying glass, focusing the light from the distant star and causing it to appear dramatically brighter for a period of days or weeks. This brightening creates a characteristic light curve, a gradual rise to maximum brightness followed by a symmetrical decline, like a cosmic lighthouse sweeping its beam across our line of sight. But the real magic happens when the lensing star has planets. As the star and its planetary system drift across our line of sight to the background star, each planet acts as an additional small lens, creating brief spikes of extra brightening that last only hours or days. These planetary signals are often tiny, causing additional brightenings of just a few %, but they carry unmistakable signatures that reveal not only the planet's presence, but also its mass and distance from its star. The beauty of gravitational microlensing lies in its sensitivity to planets that other methods cannot easily detect. While radial velocity and transit techniques work best for planets close to their stars, microlensing excels at finding worlds in wide orbits, including planets in the snow line region where water would freeze into ice. This makes microlensing particularly valuable for understanding the outer architecture of planetary systems, regions that might harbor planets similar to Jupiter and Saturn in our own solar system. The first planet discovered through microlensing was Asterisk, found in 2003, but the technique has since revealed worlds in some of the most distant and exotic locations ever detected. These planets orbit stars thousands of light years away, far beyond the reach of other detection methods. Some orbit stars in the central bulge of our galaxy, while others belong to systems in the galactic halo or even the disk of the Milky Way. What makes microlensing particularly fascinating that it provides a census of planets throughout our galaxy, not just in our immediate cosmic neighborhood. Each microlensing event offers a random sampling of whatever planetary systems happen to lie along the line of sight between us and distant background stars. This statistical approach has revealed that planets are remarkably common throughout the galaxy, with every star hosting an average of more than one planet. The technique has uncovered some truly exotic worlds. There are planets orbiting stars at the very center of our galaxy, where the intense radiation environment and close proximity to the supermassive black hole Sagittarius Asterisk create conditions unlike anywhere else in the Milky Way. There are planets around ancient stars in the galactic halo, worlds that formed when the universe was much younger and had a very different chemical composition than today. Perhaps most remarkably, microlensing has detected free-floating planets, worlds that have been ejected from their birth systems and now wander through interstellar space without orbiting any star. These cosmic nomads are invisible to almost every other detection method, but their gravitational fields can still focus the light of background stars, revealing their lonely existence in the depths of space. The precision required for microlensing observations is extraordinary in its own way. Astronomers must monitor millions of stars continuously, watching for the rare events when perfect alignment creates a microlensing brightening. Most microlensing events last only a few weeks, and the planetary signals within them may last only hours, requiring around-the-clock monitoring by networks of telescopes around the world. These global collaborations represent some of the most coordinated efforts in observational astronomy. When one telescope detects a microlensing event in progress, alerts are sent to observers worldwide, who begin intensive follow-up observations to catch any planetary signals that might occur. The international nature of these collaborations means that the Sun never sets on microlensing observations as Earth rotates. Different observatories take up the watch, ensuring continuous coverage of these fleeting events. The mathematics underlying microlensing are rooted in the most fundamental physics of space and time. Einstein's field equations describe how mass and energy curve spacetime, and the paths of light rays through this curved geometry follow the principles of general relativity with exquisite precision. Every microlensing observation provides another confirmation that our understanding of gravity and spacetime is correct, even when applied to objects and distances that Einstein could never have imagined. Modern microlensing surveys use networks of robotic telescopes that can observe millions of stars simultaneously, looking for the telltale brightening patterns that indicate a microlensing event. These surveys have revealed that microlensing events are surprisingly common. Several thousand occur each year in our galaxy, though most are caused by stars or brown dwarfs rather than planets. The technique continues to evolve with new technologies and strategies. Space-based microlensing missions can observe continuously without the interruptions caused by day and night cycles or weather, potentially detecting Earth-mass planets around stars throughout the galaxy. Future surveys will combine microlensing with other detection methods, creating comprehensive maps of planetary systems that extend from close-orbiting hot Jupiters to distant ice giants and everything in between. As you settle deeper into the comfort of your bed, consider the cosmic geometry unfolding at this very moment across our galaxy. Somewhere, a star and its family of planets are perfectly aligned with a distant background star, creating a gravitational lens that may be brightening the night sky by fractions of a percent. That brightening carries information about worlds that are farther away than almost any other known planets, yet their gravitational influence reaches across thousands of light-years to bend starlight and announce their presence. The elegance of gravitational microlensing lies in its directness. It uses nothing more than gravity and geometry to reveal the presence of distant worlds. No complex instruments or sophisticated techniques are required beyond careful photometry and patient observation. The universe itself provides the lens, the light source, and the screen on which the image is projected. We need only watch and wait for the proper alignment of celestial mechanics to reveal planets that exist in realms so distant they might as well be in another galaxy entirely. Yet even as microlensing expands our view to encompass planets throughout the Milky Way, our exploration of distant worlds requires us to look deeper than mere detection and positioning. To truly understand these alien planets, we must learn to decode the chemical messages hidden in their light, reading the molecular signatures that reveal what these distant atmospheres are made of and what conditions might exist on their surfaces. In the gentle quiet of your room, as lamplight filters through the air around you, you are witnessing something that happens on a cosmic scale around every star in the galaxy. Light interacts with matter in ways both subtle and profound, picking up chemical signatures as it passes through gases and atmospheres, carrying molecular messages across vast distances of space and time. Tonight, you learn to read these luminous letters, decoding the stories written in starlight by the atmospheres of distant worlds. Imagine holding a prism up to sunlight streaming through your window. The white light separates into a rainbow of colors, each wavelength revealing itself in the spectrum from red to violet. But look more closely at that spectrum with sensitive instruments, and you would discover something remarkable. Thin, dark lines scattered throughout the rainbow, like text written across the colors themselves. These absorption lines are the fingerprints of atoms and molecules in our sun's atmosphere, each element and compound absorbing specific wavelengths of light, leaving their signatures embedded in the solar spectrum. This same principle spectroscopy has become our most powerful tool for studying the atmospheres of exoplanets, allowing us to analyze air we will never breathe and detect molecules floating in skies we will never see. When starlight passes through a planet's atmosphere during a transit, some wavelengths are absorbed by atmospheric gases, while others pass through unimpeded. By comparing the star's spectrum during and outside of transit, astronomers can identify the specific molecules responsible for this selective absorption. The technique requires extraordinary precision. The atmospheric signal from an exoplanet typically changes the star's brightness by only a few parts per million at specific wavelengths, like trying to detect the difference in brightness between a lighthouse with and without a single colored filter held in front of it, observed from hundreds of miles away. Yet modern spectrographs can achieve exactly this level of sensitivity, opening atmospheric windows into worlds orbiting distant stars. The first atmospheric detection around an exoplanet came in 2002, when astronomers identified sodium in the atmosphere of HD 209,458b, the same hot Jupiter whose transit had been detected 3 years earlier. That single detection transformed our understanding of what was possible in exoplanet science. We could not only find these distant worlds and measure their sizes and masses, but we could actually analyze their atmospheric chemistry from across the galaxy. Since that pioneering observation, atmospheric spectroscopy has revealed an astonishing diversity of alien air. Water vapor has been detected in the atmospheres of dozens of exoplanets, from scorching hot Jupiters, where it exists as superheated steam, to potentially temperate worlds, where it might condense into clouds or even liquid droplets. Each detection of water represents a connection to one of the most essential molecules for life as we know it. Methane signatures have been found in several planetary atmospheres, particularly intriguing because methane can be produced by both geological processes and biological activity. On worlds where methane coexists with oxygen or ozone, it might indicate active biological processes, since these gases react rapidly with each other and require constant replenishment to remain present together in an atmosphere. Carbon dioxide appears in many exoplanetary spectra, especially around hot, Venus-like worlds where thick CO2 atmospheres create runaway greenhouse effects. Carbon monoxide has been detected in the upper atmospheres of several gas giants, providing clues about atmospheric chemistry and circulation patterns. Even more exotic molecules, like hydrogen sulfide and various hydrocarbons, have been identified, painting chemical portraits of worlds unlike anything in our solar system. The temperatures revealed through atmospheric spectroscopy tell stories of planetary climate and energy balance. Some hot Jupiters show dayside temperatures exceeding 2000 Kelvin, hot enough to vaporize most metals, while their night sides remain several hundred degrees cooler. This temperature difference drives powerful atmospheric circulation, creating winds that can reach thousands of kilometers per hour as heat redistributes around these tidally locked worlds. Perhaps most remarkably, spectroscopy can reveal just what molecules are present in an atmosphere, but where they exist within the atmospheric column. Different molecules absorb light most strongly at different atmospheric pressures and temperatures, allowing astronomers to probe the vertical structure of alien atmospheres. We can map temperature profiles, identify cloud layers, and even detect atmospheric escape, the process by which some planets gradually lose their atmospheres to space. The technique has revealed atmospheric phenomena that challenge our understanding of planetary science. Some planets show evidence of high-altitude hazes composed of complex organic molecules, similar to the photochemical smog that shrouds Saturn's moon Titan. Others display clear, transparent atmospheres that allow infrared radiation to escape easily into space. Still others seem to have thick, opaque cloud decks that completely obscure their deeper atmospheric layers. Transmission spectroscopy analyzing atmospheric absorption in transits represents just one approach to atmospheric characterization. Emission spectroscopy studies the infrared glow from planetary atmospheres, particularly effective for hot planets that radiate substantial thermal energy. By observing how this emission changes as planets orbit their stars, astronomers can map temperature patterns across planetary surfaces and track atmospheric circulation in real time. The James Webb Space Telescope has revolutionized atmospheric spectroscopy with unprecedented sensitivity and wavelength coverage. Its first atmospheric spectrum of an exoplanet revealed water vapor, clouds, and hazes in the atmosphere of WASP 96b with clarity that would have been impossible just a few years ago. Each new observation pushes the boundaries of what atmospheric features can be detected and analyzed across interstellar distances. Future atmospheric studies promise even more remarkable discoveries. The search for biosignature gases, molecules like oxygen, ozone, and methane that might indicate biological processes represents the holy grail of exoplanet atmospheric science. While we have not yet definitively detected biosignatures around any exoplanet, the technical capability to do so is rapidly approaching, particularly for potentially habitable worlds around nearby red dwarf stars. The chemical diversity revealed through atmospheric spectroscopy reflects the incredible range of planetary formation and evolution processes throughout the galaxy. Planets that formed in metal-rich stellar nurseries show different atmospheric compositions than those born around metal-poor stars. Worlds that migrated inward from cold outer regions carry chemical signatures of their journeys, while planets that formed in place reflect the local chemistry of their birth environments. As you rest here in the gentle darkness, consider the molecular messages traveling toward Earth at this very moment. Photons that interacted with water molecules in the atmosphere of a distant planet are racing across space, carrying that chemical signature embedded in their wavelengths. When those photons reach our telescopes and pass through their spectrographs, they will add another line to our growing library of atmospheric compositions, another chapter in the chemical story of worlds beyond our solar system. The ability to analyze alien atmospheres from such vast distances represents one of humanity's greatest intellectual achievements. We have learned to read the molecular handwriting of worlds we will never visit, to diagnose the chemical health of planetary atmospheres across the galaxy, and to search for the subtle signatures that might indicate life itself has taken hold in distant skies. Yet these atmospheric revelations are only possible because of the patient mechanical guardians that watch the stars night after night, collecting the precious photons that carry these chemical messages across the cosmic deep. The space telescopes that serve as our eyes in the cosmos have transformed from simple light-gathering instruments into sophisticated chemical laboratories, each one designed to catch and analyze the faintest atmospheric signals from worlds beyond our reach. In the stillness of your bedroom, as you settle into the quiet rhythm of approaching sleep, imagine mechanical sentinels floating in the cosmic dark, their unblinking eyes fixed on distant stars with a patience that far exceeds human capacity. These are our space telescopes, the patient guardians of discovery, who have revolutionized our understanding of worlds beyond our solar system through their tireless vigil among the stars. Tonight, you meet these remarkable instruments, not as cold machines, but as extensions of human curiosity, each one designed with a specific purpose and personality, each contributing its own unique perspective to our growing knowledge of exoplanets. They are our ambassadors to the cosmos, mechanical astronomers who never sleep, never tire, and never lose focus in their quest to reveal the secrets of distant worlds. The Kepler Space Telescope stands as perhaps the most transformative planet hunter in history. Launched in 2009, Kepler was designed with a singular mission: to stare continuously at a single patch of sky containing over 150,000 stars, monitoring their brightness with unprecedented precision to detect the tiny dimmings caused by transiting planets. For nearly 4 years, this mechanical astronomer maintained its unwavering gaze, measuring stellar brightnesses every 30 minutes with a precision that could detect changes as small as 20 parts per million. Picture Kepler's dedication. While Earth turned beneath it and seasons changed across our planet, this space telescope remained fixed on its celestial target field, a region of sky in the constellations Cygnus and Lyra covering just 0.5% of the visible sky. Its silicon detectors, cooled by the vacuum of space, captured photons that had traveled 4 decades or centuries from distant stars, sorting them by brightness and timing with robotic precision. The results were extraordinary. Kepler confirmed the existence of over 2,600 planets and identified thousands more candidates awaiting verification. It revealed that small, rocky planets are incredibly common throughout our galaxy, that multi-planet systems are the norm rather than the exception, and that planetary systems can be arranged in configurations completely unlike our own solar system. Every 30 minutes of Kepler data contained potential discoveries that would have been front-page news just decades earlier. But Kepler's greatest contribution may have been statistical. By monitoring so many stars simultaneously for so long, it provided the first reliable census of planetary populations in our galaxy. We learned that virtually every star hosts at least one planet, that Earth-sized worlds are among the most common types of planets, and that the galaxy contains billions of potentially habitable worlds. A revelation that fundamentally changed our perspective on our place in the universe. When Kepler's reaction wheels failed in 2013, threatening to end its mission, engineers devised an ingenious solution. They repurposed the spacecraft for the K2 mission, using solar radiation pressure as a virtual reaction wheel to maintain pointing stability. This extended mission discovered hundreds of additional planets around a diverse array of star types, demonstrating the adaptability and resilience built into these mechanical explorers. The Transiting Exoplanet Survey Satellite, or TESS, carries forward Kepler's legacy with a different strategy. Rather than staring at one patch of sky, TESS surveys the entire celestial sphere, monitoring the brightest stars in our cosmic neighborhood. Its 4 cameras work together to create a mosaic of observations, spending 27 days on each sector of sky before moving to the next, gradually building up a comprehensive survey of nearby planetary systems. TESS represents a new philosophy in exoplanet discovery. While Kepler searched for statistical understanding of planetary populations, TESS seeks individual worlds around specific stars that are bright enough for detailed follow-up studies. Each TESS planet discovery becomes a target for atmospheric characterization, mass measurement, and comprehensive analysis. This telescope is building a catalogue of the most accessible exoplanets worlds that future generations of astronomers will study in unprecedented detail. The precision of TESS observations is remarkable. From its orbit high above Earth, it can detect brightness changes as small as a few parts per million in stars scattered across the entire sky. Its mechanical stability is so high that it can track stellar brightness variations over months, detecting not only planetary transits, but also stellar oscillations, flares, and other astrophysical phenomena that provide context for understanding planetary environments. The James Webb Space Telescope represents the newest generation of space-based planet hunters, though its approach differs fundamentally from its predecessors. While Kepler and TESS excel at finding planets, Webb specializes in studying them. Its enormous mirror and sophisticated instruments can analyze the atmospheres of known exoplanets with unprecedented detail, revealing molecular compositions, temperature structures, and even weather patterns on distant worlds. Webb's infrared vision allows it to peer through cosmic dust and study the thermal emission from planets themselves, not just the starlight they block or reflect. Its spectroscopic capabilities can detect water vapor, carbon dioxide, methane, and dozens of other molecules in planetary atmospheres, creating chemical portraits of alien air with a precision that would have seemed impossible just a generation ago. But Webb's most ambitious goal is the search for biosignatures, atmospheric compositions that might indicate the asterisk presence of life. By studying the atmospheres of potentially habitable planets around nearby stars, Webb has the sensitivity to detect oxygen, ozone, and other gases that biological processes might produce. Each atmospheric spectrum it captures brings us closer to answering one of humanity's most profound questions: are we alone in the universe? These space telescopes operate in the ultimate frontier environment, where repair is impossible and every component must function flawlessly. For years or decades, they endure temperature extremes, radiation exposure, and the mechanical stresses of launch and deployment, all while maintaining the precision necessary to detect signals that are almost indistinguishably small from instrumental noise. The engineering challenges overcome by these missions are extraordinary. Kepler's photometric precision required thermal stability so high that the entire spacecraft was designed as a giant thermos bottle, with multiple layers of insulation protecting its sensitive detectors from temperature variations. Tests must maintain pointing accuracy better than the width of a human hair viewed from a quarter mile away, while orbiting Earth every 13.7 days. Webb operates at temperatures colder than liquid nitrogen, with its instruments cooled to just a few degrees above absolute zero to minimize thermal interference. Each telescope represents the collaborative effort of thousands of engineers, scientists, and technicians working across multiple countries and decades. Their designs evolved through countless iterations, their instruments tested and retested in specialized facilities that simulate the harsh environment of space. Every component was scrutinized for reliability, every software algorithm verified against multiple failure scenarios. The data these telescopes collect flows back to Earth through NASA's Deep Space Network, a global array of giant radio antennas that maintain contact with distant spacecraft. This data stream contains the raw material of Discovery brightness measurements, spectra, and images that must be processed, analyzed, and interpreted by teams of scientists working around the world. As you drift towards sleep tonight, consider that these mechanical guardians are at work at this very moment, their electronic eyes fixed on distant stars, their detectors counting photons that left those stars years ago. Somewhere in their data streams may be the signals that will reveal tomorrow's exoplanet discoveries, new worlds that will expand our understanding of planetary formation, atmospheric chemistry, and perhaps even the prevalence of life throughout the galaxy. These space telescopes have transformed astronomy from a passive science of observation to an active hunt for discovery. They have automated the process of cosmic exploration, allowing us to survey thousands of stars simultaneously with a thoroughness and precision that no human observer could match. They are the patient guardians who never sleep, never blink, and never lose interest in the subtle signals that announce the presence of worlds beyond our solar system. Through their electronic eyes, we have begun to map the true diversity and abundance of planetary systems throughout our cosmic neighborhood, setting the stage for even more detailed studies of individual worlds and their potential to harbor the chemistry of life. As you settle into the deepening quiet of your evening, imagine an artist working on a vast canvas, adding layer upon layer of detail with different brushes and techniques. Each stroke reveals new aspects of the subject, building from rough outline to intricate portrait. Tonight, you discover how astronomers work as cosmic artists, using dozens of subtle techniques to paint detailed portraits of worlds they will never visit, building comprehensive maps of planetary systems from fragments of light that have traveled across the galaxy. The art of characterizing exoplanets goes far beyond simple detection. Once we know a planet exists, an entire toolkit of observational techniques allows us to determine its physical properties, atmospheric composition, orbital characteristics, and even its evolutionary history. Each method adds another dimension to our understanding, transforming distant points of light into fully realized worlds with distinct personalities and stories. Transit timing variations represent one of the most elegant techniques for studying planetary systems in detail. When a planet orbits its star in perfect isolation, its transits occur with clockwork precision, each passage across the stellar disk happening at exactly predictable intervals. But when multiple planets share the same system, their gravitational interactions create subtle timing anomalies that reveal the presence of additional worlds and provide exquisite measurements of planetary masses. Picture a cosmic ballet where multiple dancers influence each other's movements through invisible threads of gravitational attraction. A large planet in an outer orbit will periodically tug on an inner planet, sometimes accelerating it slightly in its orbit and causing it to arrive at transit a few minutes early, other times decelerating it and making it arrive late. These timing variations, measured over dozens of transits, can reveal not only the presence of non-transiting planets, but their masses, orbital periods, and gravitational relationships with remarkable precision. The TRAPPIST-1 system provides a spectacular example of this technique in action. This system of 7 Earth-sized planets orbits so close to each other that their mutual gravitational influence creates a complex symphony of timing variations. Each planet's transit timing is affected by the gravitational tugs of all the others, creating a multi-layered puzzle that astronomers have solved to determine the individual masses of all 7 worlds and map their gravitational architecture. In extraordinary detail, stellar activity analysis opens another window into planetary characterization by studying how planets interact with their host stars' magnetic fields and stellar winds. Some planets orbit so close to their stars that they experience extreme stellar radiation and magnetic interactions, creating detectable effects in stellar spectra and brightness variations. Hot Jupiters can induce stellar activity through magnetic reconnection events, while planets with extended atmospheres may leave observable trails as stellar winds strip away their outer layers. The technique of eclipse photometry allows astronomers to measure the thermal emission from exoplanets directly. When a planet passes behind its star as viewed from Earth as secondary eclipse, the combined light from star and planet drops slightly as the planet's thermal glow is blocked. By measuring this tiny decrease in brightness at infrared wavelengths, astronomers can determine the planet's temperature, study its atmospheric circulation, and even map temperature variations across its surface. These thermal measurements have revealed some of the most extreme environments in the known galaxy. Hot Jupiters show dayside temperatures exceeding 2000 Kelvin, hot enough to vaporize metals and create atmospheric winds of several thousand kilometers per hour. Some planets are so hot that their atmospheres rain molten rock, while others show evidence of temperature inversions, where upper atmospheric layers are actually hotter than lower regions due to exotic chemical processes. Phase curve observations track how planetary brightness changes throughout an entire orbit, revealing information about atmospheric circulation, heat redistribution, and surface properties. As a planet orbits its star, we see different fractions of its illuminated hemisphere, similar to how the Moon shows phases. By measuring these subtle brightness variations, astronomers can map temperature patterns across planetary surfaces and study how efficiently heat is transported from day sides to night sides. Atmospheric escape studies examine how planets lose their atmospheres to space in a geological time. High-energy radiation from young, active stars can heat planetary atmospheres to such extreme temperatures that atmospheric gases achieve escape velocity and stream away into space. These escaping atmospheres create extended comet-like tails that can be detected through ultraviolet spectroscopy, providing insights into planetary evolution and the long-term habitability of worlds around active stars. The technique of astroseismology studying stellar oscillations provides precise measurements of stellar properties that are crucial for accurate planetary characterization. Stars ring like bells with acoustic oscillations that depend on their internal structure, mass, age, and composition. By measuring these stellar vibrations, astronomers can determine stellar properties with extraordinary precision, which in turn allows more accurate calculations of planetary sizes, masses, and orbital distances. Astrometry, the precise measurement of stellar positions, offers another approach to planetary detection and characterization. As planets orbit their stars, they cause tiny wobbles in stellar position that can be measured with space-based telescopes equipped with ultra-precise positioning systems. While these positional shifts are incredibly small, measured in microarcseconds, they provide direct measurements of planetary masses and orbital inclinations that complement other detection methods. The study of planetary atmospheres through transmission and emission spectroscopy has evolved into an incredibly sophisticated field. Different atmospheric layers absorb and emit light at different wavelengths, allowing astronomers to probe the vertical structure of alien atmospheres. Temperature profiles, pressure gradients, cloud compositions, and atmospheric circulation patterns can all be inferred from careful analysis of how planetary spectra change with wavelength and orbital phase. Magnetic field detection around exoplanets represents one of the newest frontiers in planetary characterization. Strong planetary magnetic fields can interact with stellar winds to create radio emissions detectable from Earth. While no confirmed radio detection of an exoplanetic magnetic field has yet been made, several candidates show promising signals that might represent our first glimpse of magnetic activity around distant worlds. The combination of multiple characterization techniques creates comprehensive portraits of individual planetary systems. By measuring masses through radial velocity, sizes through transits, atmospheric compositions through spectroscopy, and thermal properties through eclipse observations, astronomers can determine planetary densities, surface gravities, atmospheric scale heights, and even make educated guesses about surface conditions and potential habitability. These detailed characterizations have revealed the incredible diversity of planetary worlds throughout our galaxy. There are planets with densities lower than Cork, indicating fluffy atmospheres extended far into space. There are superdense worlds with compositions dominated by iron and other heavy metals. There are planets with atmospheric pressures hundreds of times greater than Earth's, and others with atmospheres so tenuous they barely qualify as atmosphere at all. The orbital architectures revealed through precise characterization studies show planetary systems arranged in configurations that challenge our understanding of planetary formation. There are planets in extremely elliptical orbits that experience dramatic seasonal variations. There are systems where multiple planets share nearly identical orbital periods, locked in complex gravitational resonances that stabilize their motions over billions of years. As you rest here in the gentle darkness, consider that each technique described tonight adds another layer of detail to our cosmic portrait gallery. Every observation, every spectrum, every timing measurement contributes to our growing understanding of how planets form, evolve, and interact with their stellar environments. We are mapping not just the locations of distant worlds, but their physical properties, atmospheric compositions, and evolutionary histories. The techniques we use to characterize exoplanets continue to evolve and improve, driven by advances in detector technology, data analysis methods, and theoretical understanding. Each new capability opens previously inaccessible aspects of planetary science, allowing us to study phenomena that were purely theoretical just a few years ago. Through these combined efforts, we are creating the first comprehensive census of planetary diversity in our cosmic neighborhood, setting the stage for the ultimate question that drives much of this research: the search for worlds that might harbor life and the quest to understand our place in a universe that appears to be filled with planets beyond our wildest early IMAGI and INGS. In the deepening tranquility of your rest, as your breathing settles into the gentle rhythm of approaching sleep, you arrive at the conclusion of a remarkable journey through the cosmos. Tonight, you stand metaphorically at the threshold of an infinite library, a vast collection of worlds that stretches across our galaxy and beyond, each planet a unique volume in the greatest story ever told, the story of cosmic evolution and the endless creativity of planetary formation. Since that first confirmed exoplanet around a Sun-like star in 1995, our catalogue of known worlds has grown from a single entry to over 5,000 confirmed planets, with thousands more candidates awaiting verification. But these confirmed discoveries represent only the tiniest fraction of the planets that exist in our galaxy. Current estimates suggest that virtually every star in the Milky Way hosts at least one planet, and many stars harbor entire families of worlds. With over 100 billion stars in our galaxy alone, the total number of planets may exceed 1 trillion, a number so vast it challenges human comprehension. Consider the profound shift in perspective this represents. For most of human history, we knew of only 6 planets: Mercury, Venus, Earth, Mars, Jupiter, and Saturn. Even after the discoveries of Uranus and Neptune expanded our solar system to 8 worlds, planets remained rare and precious objects in our understanding of the universe. Now we know that planets are among the most common objects in the cosmos, more numerous than stars themselves. Scattered throughout every region of our galaxy, grains of sand on an infinite beach. The diversity revealed in our growing planetary catalogue exceeds even the most imaginative early predictions. There are worlds where the surface temperature exceeds 2,000 degrees Celsius, hot enough to melt most metals, and others where the atmosphere has frozen solid onto the planetary surface. There are planets with years that last just a few hours, and others with orbital periods measured in thousands of Earth years. There are worlds orbiting binary stars, experiencing double sunsets and complex seasonal cycles that vary with the orbital dance of their stellar parents. The size range of discovered planets spans from worlds smaller than Mercury to gas giants larger than Jupiter. But perhaps most surprisingly, the most common planetary type in our galaxy appears to be one that doesn't exist in our own solar system: super-Earths, rocky worlds with masses between Earth and Neptune. These intermediate-sized planets represent a cosmic middle ground between small, rocky worlds and large, gaseous ones, with properties we are only beginning to understand. The architectures of planetary systems show remarkable variety. Some stars host single, massive planets in wide, elliptical orbits. Others are surrounded by closely packed families of worlds orbiting closer to their star than Mercury orbits our Sun. There are systems where planets exist in perfect orbital resonances, their gravitational interactions creating stable configurations that have persisted for billions of years. There are also systems that appear chaotic, with planets in crossing orbits or highly inclined planes that suggest violent, dynamical histories. Many of the most intriguing discoveries challenge our understanding of planetary formation and evolution. Hot Jupiter's massive gas giants, orbiting extremely close to their stars, were among the first exoplanets discovered. Yet their existence came as a complete surprise. Current theory suggests these worlds formed in the cold outer regions of their systems and then migrated inward through gravitational interactions with protoplanetary disks or other planets. Their discovery revolutionized our understanding of planetary migration and system evolution. The habitability question has become one of the most compelling aspects of exoplanet research. Hundreds of planets have been discovered in the habitable zones of their stars, the orbital distances where liquid water could potentially exist on planetary surfaces. These potentially habitable worlds range from small, rocky planets around red dwarf stars to larger super-Earths orbiting Sun-like stars. Each discovery brings us closer to answering the profound question of whether Earth-like conditions exist elsewhere in the universe. But habitability extends beyond simple orbital distance. The thickness of planetary atmospheres, the strength of magnetic fields, the composition of stellar radiation, and the stability of orbital and rotational properties all influence whether a world might support liquid water and potentially life. Some planets in habitable zones may be too hot due to runaway greenhouse effects, while others might be frozen due to insufficient atmospheric insulation. The study of planetary habitability has become a complex, multidisciplinary science that combines astronomy, planetary science, atmospheric physics, and even biology. The search for biosignatures in exoplanetary atmospheres represents the next great frontier in this field. While we have not yet detected definitive signs of life around any exoplanet, the technical capability to do so is rapidly approaching. The combination of oxygen and methane in an atmosphere, certain ratios of atmospheric gases, or the detection of industrial pollutants could potentially indicate biological or even technological activity on distant worlds. As you rest here, the quiet darkness, consider that our galaxy is likely teeming with worlds beyond our current ability to detect. Earth-sized planets around sun-like stars remain at the edge of our detection capabilities, requiring multiple transits observed over several years to confirm their existence. Smaller worlds, planets in wide orbits, and worlds around faint stars may remain undiscovered for years or decades to come. The statistical understanding gained from current surveys suggests that small, rocky planets are incredibly common throughout the galaxy. If even a small fraction of these worlds possess the conditions necessary for life, the biological implications are staggering. We may live in a universe where life is not rare and precious, but common and abundant, evolving independently on millions or billions of worlds throughout our cosmic neighborhood. Future surveys will expand our planetary census dramatically. The Nancy Grace Roman Space Telescope will use gravitational microlensing to detect planets throughout the galaxy, including Earth-sized worlds in Earth-like orbits around sun-like stars. Ground-based extremely large telescopes will directly image and characterize planets around nearby stars. Advanced coronagraph missions will photograph Earth-like worlds and analyze their atmospheric compositions for signs of biological activity. The techniques we use to study exoplanets continue to evolve rapidly. Machine learning algorithms are being developed to identify planetary signals in data to asterisk. Complex for human analysis. New theoretical models help predict which types of planets might form around different stellar types and in different galactic environments. Improved laboratory measurements of atmospheric chemistry provide better templates for interpreting spectroscopic observations of distant worlds. Each new discovery adds another entry to our cosmic library, another chapter in the ongoing story of planetary formation and evolution. Some worlds tell stories of violent birth in the chaotic early epochs of stellar formation. Others reveal tales of gradual evolution over billions of years, their atmospheres slowly changing as their stars aged and brightened. Still others show evidence of catastrophic events, massive impacts, atmospheric loss, or gravitational disruption by neighboring planets. The pace of discovery continues to accelerate. New planets are confirmed almost daily, and major surveys are identifying candidate worlds faster than they can be thoroughly studied. We are living through the golden age of exoplanet discovery, a time when each month brings revelations that would have been front-page news just a generation ago. But perhaps the most profound realization from our growing catalogue of worlds is not the diversity of planetary types or the complexity of their formation processes, but the simple fact that planets exist at all. The universe could have been a cold, empty place populated only by stars and the remnants of stellar death. Instead, we find it filled with worlds, rocky planets, and gas giants, hot Jupiters and frozen ice balls, potentially habitable worlds and exotic chemistries we never imagined. As your thoughts drift toward the edge of sleep, let yourself rest in the knowledge that you are part of a remarkable moment in human history. For the first time in our species' existence, we know with certainty that our planet is not unique, that worlds beyond our solar system exist in vast profusion throughout the galaxy. We have learned to read the subtle signals of these distant worlds, to analyze their atmospheres, to map their orbits, and to study their properties across interstellar distances. Each star you might glimpse through your window likely hosts its own family of worlds, each one shaped by the unique circumstances of its formation and evolution. Somewhere among those distant planetary systems, may be worlds where conditions have allowed life to emerge and flourish, where alien skies host foreign constellations, where the chemistry of life has written different stories in different atmospheric compositions. The infinite library of worlds awaits our continued exploration. Each planet a unique story of cosmic evolution, each discovery a new chapter in our understanding of how the universe creates and sustains the conditions for complexity, chemistry, and perhaps even consciousness. In mapping these invisible worlds across the galaxy, we have begun to map our own place in the vast community of planets that fills the cosmos, no longer alone in the universe, but part of an infinite family of worlds that orbit the stars, asterisk,